This is a walkthrough of Problem 2 on Exam 2 of Module 8 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 2, two parallel wires right here shown in cross section. They are perpendicular to the plane of the page, going a long way into and out of the page. They are double infinite with respect to this point, in respect to any point in the plane of the page. The top wire is 8 centimeters above the bottom wire. Top wire carries 7 amps into the page, hence this X notation for into the page. The bottom wire carries 4 amps out of the page, hence this notation for out of the page. Part A, where is the magnetic field 0? Okay, let's think about this before we go on to Part B. The first thing we have to do is consider which region of space where the field might be 0. So we're going to use the right-hand rule, and we're going to draw the field lines by sticking our thumb along the direction of the current. So for the bottom wire, we stick our thumb directly out of the page, and we curl our fingers around, and that is counterclockwise. So this wire makes magnetic field lines going this way, counterclockwise. For the top wire, we have to stick our thumb into the page, so it produces field lines that are clockwise, like this. All right, so where is the field 0? Between the wires, the bottom wire produces a field to the right, to the left, that way. Between the wires, the top wire also produces a field to the left. There's no way the fields can cancel in here because they're in the same direction. What about above the wires? The top wire makes a field to the right above the wire. The bottom wire makes a field to the left above the wire. The fields are in opposite directions. However, this wire carries 7 amps. This wire carries 4 amps. The field produced by the top wire is always going to be greater than the field produced by the bottom wire above the top wire because the top wire carries more current and it is closer. Below the wires, the bottom wire produces a field to the right. The top wire produces a field to the left. So somewhere down here they're going to cancel. The fact that the top wire has more current will be offset by the fact that it's farther away. So somewhere below the wires, the field is 0. Well, we'll start by defining some distance x at which the field is 0. Field is 0 right here. We don't know what x is. We have to calculate it. The magnitude of the fields are equal. The directions are opposite, so we can set their magnitudes equal. We know what the equation is. Mu naught I over 4 pi a. They're double infinite, so we put a 2 in there. Now we plug in the equations. Top wire has a current of 7 amps, and it is 8 centimeters plus x away from the point where we're measuring the field. The distance between the wires is 8 centimeters. The top wire is 8 centimeters plus x away from this point. The bottom wire carries a current of 4 amps, and it is x away. There's the 4. The distance is x. A lot of canceling going on here. Cancel the amps, cancel the mu naughts, cancel the 4 pi's, cross multiply, cancel the 2's. We have 7x is 4 times 8 centimeters plus x. We can distribute the 4. We get 32 centimeters plus 4x. Subtracting 4x from both sides gives 3x equals 32 centimeters. X is 10.7 centimeters. The answer is the magnetic field is 0, 10.7 centimeters directly below the bottom wire. Now we can tackle part B. What is the magnetic field at a point that is 6 centimeters to the right of the bottom wire, right here? This is a multi-step problem. We have to be careful with each step. First, let's get the field directions. And to do that, it's best to draw the perpendicular distances first, because the magnetic field from a wire at a point, any point, this point, that point, this point, that point, that point, is perpendicular to the distance between the wire and the point. To see what we mean, we'll put in the distances. There's the distance from the wire to the point. We can imagine a bunch of concentric circles going around, and when it gets here, it's going straight up. We know that the field is perpendicular to the distance. It's either straight up or straight down, depending on the direction of the current. If we use the right-hand rule, we see it's straight up. This guy, let's put in this distance. So the magnetic field produced by this wire is either in this direction or that direction, based on the direction of the current. All right, so we got the distances. Let's put in the fields. This guy is straight up. B from the bottom wire is straight up. If I stick my thumb into the page and curl it around, I see that it's down this way. So this one's right here. It's a right angle to that distance, like that. That's a right angle. This is a right angle. Okay, we got the directions. Carefully. We got it right. Now we can get the magnitudes. How long are these vectors? The magnetic field from the bottom wire, U naught I over 4 pi a times 2, because it's double infinite. The distance is given as 6 centimeters, converting that to meters. Crunching the numbers, we get 13.3 microtesla. That's the length of this vector right here. Now we can do the top wire. The direction's upward. We need this distance. That's 6 centimeters. That's 8 centimeters. 6 squared is 36. 8 squared is 64. 64 plus 36 is 100. The square root of 100 is 10. That distance is 10 centimeters. The magnitude is U naught I over 4 pi a times 2. There's mu naught. The current is 7 amps. The distance between the wire and the point at which we're measuring the field is 10 centimeters, which is 0.1 meters. And we get 14 microtesla for this length. Slightly longer than that. To add up these vectors, we have to split this B field from the top wire into horizontal and vertical components. They're both negative. Negative in the x, negative in the y. First, we need this angle. What's the angle this makes with the horizontal? That's the same as this angle right here, and that's the arctangent of 6/8. We can calculate this angle, and let's put it in. Theta is 36.87 degrees. Now we can get the B field in the x direction, minus 14 microtesla cosine 36.87 degrees. And so this is minus 11.2. In the y direction, we use sine, and that's minus 8.4. 8.4 microtesla downward, this component right here. And now we are ready to get the net field in the x direction and y direction. B sub x only has one contribution. That's minus 11.2 microtesla. B sub y has B bottom up, which is 13.3, and B top sub y down, which is 8.4. 13.3 up, 8.4 down gives 4.93 up. We can use the Pythagorean theorem again to get the magnitude of the field. 12.2 microtesla. Somewhere like this. And we need the direction. The y is plus 4.93. The x is 11.2 that way. To the left, the angle is 23.8 degrees. So the answer is the magnetic field is 12.2 microtesla at an angle of 23.8 degrees above the negative x-axis. It's always a good idea to put the vector in there to see if it makes sense. And there it is. And you can see that it makes sense if you add B top and B bottom by using the head to tail method. You can take B bottom and stick it right here. You'll get that. Or you can take B top and stick it right here and get the net magnetic field right here. That's the answer to problem 2.